A very good morning to all of you. In this first part of today's lecture, we are going to discuss moving axis rotations. Remember, we are doing rotational motion, and the examples of rotations that we did so far were all which we sometimes call as pure rotation. In a pure rotation, the axis of rotation is fixed in space and all the particles of the rigid body, they move in concentric circles around that axis of rotation. But there are many examples where axis is moving. So for example, if you toss an object in air, say maybe a small little rod or something, or a pencil or a pen, if you toss it in air, by flipping it with your fingers, it will rotate and fall down. So that is an example of a rotational motion where axis is moving. Other type of example which is very classic is rolling bodies. So when the bodies roll, say tires of a vehicle, then the axis of rotation also moves forward or backward. So we are going to take these class of rotational motion in today's lecture. There is one more class of rotational motion which involves the precision of spinning, precision of axis that we are going to take in the next class. So we are going to talk about rolling bodies and the role of friction in rolling bodies. We'll try to take some other examples also. So the moving axis rotation, I gave you two examples, a baton tossed or a small little linear rod like object flipped and tossed in air. It will rotate and fall down. That is an example of moving axis rotation. Another example is a rolling body where the axis is moving, the vehicle of a car, or if you are familiar with the yo-yo, then the axis of yo-yo also, yo-yo rotates along a string, goes down, comes up. So the axis moves up and down. Any moving axis rotation can be seen as a combination of translational motion of the center of mass and the rotation about an axis through the center of mass. So it can be seen as the combination of two motions. Translational motion of the center of mass means assuming that the center of mass of the particles or center of mass of the body is moving on a line. So this is one type of motion that the body may be undergoing. Plus, body is performing pure rotation about an axis through the center of mass. So this is an example. A small wrench in my example is tossed in air. You can see that its orientation changes as it gets airborne. So here, by the time it reaches from here to here, it its orientation changes by 180 degrees. So it is in a translational motion as if the center of mass is moving about this dotted line, but it is also kind of performing a rotation and it has rotated through 180 degree. So it can be seen as a rotation by 180 degree plus a translation about the center of mass, about this dotted line. How would the energy of a rotating body or a moving axis rotation looks like. So the kinetic energy of rotation we have already seen. It is half I moment of inertia about center of mass into omega square plus kinetic energy of translation half m and the square of the velocity of center of mass. So this equation becomes very obvious equation. You have two components of kinetic energy, one due to pure rotation, half I omega square. Remember here, rotation is about the center of mass. So the moment of inertia has to be about the center of mass and the kinetic energy of translation. A rigorous proof of this equation is also very simple and straightforward. I would recommend you all to explore it on your own. The other component of energy that the rigid body that may still possess is potential energy. So potential energy is typically written as mgy or mgy of center of mass, where y of center of mass gives its height from a reference point. So that's how you address the energy issue in moving axis rotations. Let's take an example of a class of motion which is called rolling without slipping. We have already seen one example of a tossed body. How a tossed body which is also rotating can be seen as a combination of rotational motion and translational motion. Let's now see a rolling body. So I have a wheel which is rolling on a surface. Now typically if both the points are rigid, both the bodies are rigid, that is if the surface is also rigid and the rolling body is also rigid, and this is a very important assumption. I will discuss towards the end what will happen if this assumption breaks down. So if both the bodies are rigid bodies, in that case the contact point here is a single point, one dimensional point, and this point is momentarily at rest. Why would it be at rest? Just imagine if this point is not momentarily at rest, then the rigid body, rotating body will tend to slip upon the lower surface, and that won't be called as rolling without slipping. So if I'm taking a class of rotation which is rolling without slipping, then the point P should not slip. That means speed of the point P has to be same as the speed of the ground surface. Now if the ground surface is at rest, that means this also should be momentarily at rest. So for the rotating body, the speed of this particle should be a negative of, or velocity of particle p should be a negative of velocity of center of mass. As the body rolls, the center of mass will move forward. So the velocity of center of mass can be shown by vcm. It is in the forward direction. As this is in the forward direction, due all the particles of this body will have same forward direction motion, but because of rotation this particle will have some velocity in the backward direction. This backward direction of velocity of particle p has to be equal to the forward direction of the velocity of center of mass. So the vector vp or velocity vector for particle p has to be negative of velocity vector of center of mass. Now, velocity vector of magnitude of the velocity for particle p is r omega, as we are all familiar. R is the radius, omega is the angular velocity. Therefore, the velocity of center of mass has to be equal to r omega. So please don't get confused in the term. This is linear velocity of center of mass, which is this term. What we have proved in earlier class is linear velocity of a tangential point or linear velocity of a peripheral point, which is Vp, which is r omega. What the simple argument here means is the linear velocity of a point which is at the periphery is opposite of the linear velocity of center of mass in direction, and in magnitude they are equal. Why? Because unless these conditions are satisfied, the net speed of particle p will not be zero and it will not be at rest momentarily. Since it has to come to rest with respect to ground, its forward velocity and the reverse velocity vectors cancel out. So if this situation is satisfied, then it is called a rolling without slipping. The rolling with slipping, how would it look like? So maybe if there is not enough friction, say you are on a sandy surface or if there is ice, the wheel will rotate but it will not move forward. That is one example of slipping. It will start slipping, or sometimes it is also called as skidding, etc. Sometimes it may not rotate and just slip forward if there is not enough friction. So another way to check rolling with slipping is, or rolling without slipping is, in one rotation how much distance the wheel will travel. So if it is rolling without slipping, then the distance traveled by the wheel on the road has to be equal to, in one rotation, has to be equal to one circumference. So when this particle rolls and comes back at some further point, the distance traveled on the road surface is 2 pi r. So if that is satisfied, again it is rolling without slipping. So here rolling without slipping I have shown as a sum of translational motion and the rotation about center of mass. You can see that this is my wheel schematically represented. I take 4 points here, 1, 2, 3, 4. Since the center of mass has linear velocity Vcm, all these 4 points should have the same linear velocity. Otherwise, the body will not stay rigid. So this is the translational component of the motion. It can also seen as some translational component plus some of rotational component. This pure rotation is happening about its axis. So it is just rotating like this. So each particle will have velocity like this. The particle at the top will have the velocity in forward direction, Vcm. We have just seen that Vcm has to be equal to r omega. This also has a tangential velocity. Again, magnitude is Vcm, but remember, for this particle the direction is downward. For this particle, magnitude is again Vcm, but we have just seen the direction will be negative, that is opposite direction. For this particle, the direction is upward, magnitude is again Vcm. Now if you superimpose the two diagrams, that is this diagram and this diagram, then you get the net rotation. So once you superimpose the velocity, here the center of mass is fixed, here center of mass has velocity Vcm. So after superimposing, center of mass will get a velocity vcm. This point is moving in the opposite direction, that is backward direction. Here it is moving in forward direction. After superposition, they will cancel out, and this is momentarily at rest. Interestingly, the topmost point is moving in the same direction with the same speed in both the situation. So they will add up, and the highest point will move at highest point will move with the speed which is 2 times v of center of mass. Look at these 2 points. So this point has one vector upward and one vector rightward. So the resultant of this and this will work in this direction, which is 45-degree with the horizontal, and the resultant of this one and downward will work in this direction, which is again 45-degree in the negative sense from the horizontal. So this is how you can combine the rolling and slipping motion together. I'm sorry, you can combine translational and rotational motion together. Let's talk about rolling friction, because this is sometimes very creates a lot of confusion and challenge. So let's say a rigid body is rolling on a rigid surface. The forces acting on the rigid body are mg working downward. If both the bodies are rigid, then this is the normal reaction working here and the friction working backward. So for a pair of rigid bodies, the line then this point is a very well defined contact point, very small point. It does not have dimensions, zero dimensional. Remember, the geometrically a point is a design which does not have a dimension. So this point is really a point, and this point is going to be in line with the center of mass. So the normal reaction works towards the center of mass. So at the center of mass, normal reaction does not apply any torque because it does not have a lever arm. There is no R here. Similarly, mg does not apply a torque on the center of mass. But friction does apply the center of mass. So here friction is working this way and it is applying, this is the lever arm from the center and it will apply a torque. What kind of friction would it be? Would it be a kinetic friction or would it be a static friction? The answer to this question is very straightforward. If you have followed the discussion so far, then you know that this is a static friction. Why static friction? Because this point is at rest momentarily. So the friction you will use over here is a static friction. So yes, so the torque here, that's right, Savio. That's correct. That's right, Ranveer. So torque here is due to the static friction. This torque also, this friction force will apply a torque because there is a lever arm, and this friction force does not do any work on the sphere. Okay, because we will come to that part in a while. It is perpendicular to the, we will come to that work in rotation part in some time. However, in real rigid bodies, this situation is not as straightforward as I have depicted here. Because ideal rigid bodies are just ideal. The real pair of bodies are not, even though we call them rigid, they are not ideally rigid bodies. Since they are not rigid bodies, they deform. Here is an example of the surface being deformed. So because of the weight of the sphere, the surface will get little bit deformed. Even if it is not seen with naked eye, microscopically it will still slightly. Once the deformation happens, then the surface piles up in the front of the sphere. There will be slightly more mass aggregation in front than towards the back side, and the sphere rides in a shallow trench. So there's a trench kind of thing in which the sphere rides, and because of which the resultant contact is not a point but is an area. All these normal forces are spread over some area now. They are no longer restricted to a well defined point. So in that case, you will have a lot of normal vector here, 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 here. I can take a resultant of all the normal vector and draw at one place. But remember, this normal force will no longer pass through the center of mass. It is no longer in the line of the center of mass. And therefore, the normal force will get a lever arm. Look at the line of action of normal force. This is the line of action. And this is my lever arm. So as a result, look at it, the friction will apply a clockwise torque while the normal reaction will apply an anti-clockwise torque. So it opposes the rotation. The normal reaction is going to oppose the rotation in real bodies. That is why the bodies will eventually come to rest. If you roll a sphere on the ground, eventually after traveling some distance, it comes to rest. If you roll a football on the ground, after traveling some distance, it comes to rest. So this is the reason, and this phenomena or this effect is normally referred as the effect of rolling friction. It is a small, but it is there. It is there enough to stop the rolling bodies eventually. Just that if more rigid the surfaces are, this phenomena would be very negligible. Now I have shown the deformation of the surface. The rigid body may itself get deformed sometimes. For example, if it's a tire or something, and there may be some sliding in this trench that may happen. The rigid body may slide in the trench. There may be it may not remain 100% static, and because of all these, some energy is lost again. So all these combined phenomena, they are normally referred as rolling friction. And as I said, it can also occur if the rolling body is deformable, that just like an automobile tire. So tire of a car, tire of a cycle, when it rolls on the road surface, typically road surface is tougher than the tire. So tires get deformed, and they introduce these kind of friction effects, which is called rolling friction. So I hope the concept of rolling friction is very clear. Important point that we have to remember is the more rigid the bodies are, the more negligible is the rolling friction. Rolling friction itself is very, very less compared to the static and the kinetic friction for the same pair of bodies. The amount of energy lost due to rolling is very less compared to sliding. That is why we have invented rolling, or invention of wheel has become one of the hallmark of progress of modern societies, that has actually enabled us to conserve lot of energy for locomotion, for moving from one point to other. So the dynamics of combined translation and rotation. So Newton's second law applies here. Newton's second law has two ways of writing, we have seen in previous lectures. One is the for translational motion, sigma f external is equal to m into acceleration. For a rigid body, it is the acceleration of the center of mass, remember that. Now this force will have, it's a vector equation. So this equation will have three components. So x component of force, sum of x component of force will give me sum of x component of acceleration. Sum of y component of force will give me sum of y component of acceleration, so on and so forth. Similarly, the Newton's second law for rotational motion will also apply. This is an analog of Newton's second law for rotation. Total external torque is equal to moment of inertia of the body about its center of mass into alpha, where alpha is angular acceleration. So again, this will apply. There can be two types of torque, remember, clockwise or anti-clockwise. So you have to take the sum of all the torques. To apply the second equation, there are two conditions must be satisfied. The axis through the center of mass must be an axis of symmetry. So that is another important. And the next is the axis must not change direction. Axis, when the translation is happening, the axis must move parallel to itself. That is why in the beginning I told you the bodies which undergo precisional motion we will exclude here, like rotating top or a gyroscope, that we will discuss in the next class. Typically, when the friction works on a rigid body, the friction gives mass into acceleration. Typically, this role of this friction is to provide a negative acceleration on the body so that its linear speed goes on decreasing for a rolling body. Also, the friction provides the torque as we have seen in the previous example, and it aids to the rotation. So the body will go on rotating because of the torque due to friction. So the two equations for all rolling body situation has to be written simultaneously. You cannot write them, you cannot just write one equation and go on. Both the equation has to be written simultaneously and then problem should be solved. So we will see this when we solve the problems. With this, we finish this part of the lecture.